All right, in this lesson we're going to talk about second order linear differential equations, and this lesson is supposed to be an introduction. So this is a generic second order. Notice order means the number of the highest derivative, so second derivative means second order. So p of x dy squared dx squared plus q of x dy dx plus r of x y of x equals g of x. We're going to probably in the future simplify that and just say y double prime and y prime there and y there. Okay, there's two main types of these types of differential equations. So this is a type of second order differential equation. It's not every single one. There's lots of different types. But this is the most simple and the most common. All right, so to further type it, if g of x equals 0, we're going to give this guy another name. We're going to say that the dE is homogeneous. And just a point of contention, I'm going to move my hand here so you can see what I'm writing. That is not homogeneous. There is an extra E right there. This is homogeneous. And it does not mean the same thing as homogeneous does anyway. Okay? Otherwise, if g of x is not equal to 0, so if we have a function on the right hand side that's not equal to 0, then the dE is, make a guess, sorry, it's not heterogeneous. The dE is non-homogeneous. Okay, so as far as solving differential equations, we're going to start with the homogeneous ones and then work our way to the non-homogeneous ones. And the non-homogeneous solutions are going to depend on the homogeneous solutions. Okay, so specifically, we're going to look at this case when this p of x, q of x, and r of x are actually constants. So our differential equations that we're going to start with are going to look like this. So a y double prime plus by prime plus cy equals 0. So that's a generic second order linear homogeneous differential equation with constant coefficients. Okay, so the first thing we should know, so this is just fact stuff here. I'm not going to get into proving this for you or anything like that. The solution set of any second order, that's not just these, differential equation is a two-dimensional vector space. Okay, let me let you take in that sentence and I'll step back here for a second. So, two-dimensional vector space. So what does that mean? So, that is, there are two linearly independent solutions to any homogeneous second order dE. And once again, let me move my hand back from that so you can get in that sentence and sort of see what I'm saying. Now, I'll start with a definition of linear independence, but then we'll move on to how we're really going to figure that out. Okay? So y1 and y2 are two, and technically these guys are vectors. So when we're talking about linear independence and a vector space, we're really talking about vectors, but these are really functions that act like vectors. These are two linearly independent functions if, okay, so here's the definition of linear independence. When C1 y1 plus C2 y2 equals 0, so this is what we call right there, the left-hand side of that is what we call a linear combination. So when that's the case, C1 and C2 equal 0. So the only way to make that linear combination equal to 0 is if the constants in front of the functions are 0. Okay, certainly if that's true, that the constants are 0, the whole thing is 0. But if they're not linearly independent, there might be other constants that might make that work. And just another sort of way to think about linear independence just for two-dimensional vector spaces. This doesn't work in general. So let's say if not, let's say if basically we have C1 Y1 plus C2 Y2 equals 0, but C1 and C2 are not 0, then we can solve for Y1, and we get that Y1 is minus C2 over C1 Y2. Okay, so that means what? That means Y1 is a scalar multiple of Y2. Okay, now I've got one other thing to talk about, and this is how we're actually going to prove things are linearly independent. So I'm going to define this thing called the Wronskian, and it's named after somebody, and it's probably spelled in 3 different books 3 different ways. So this is the way I've always seen it spelled. Well, let me take that back. Instead of the SK, I think it's Russian, so sometimes I've seen an X there or something like that, who knows. But I'm going to spell it this way. So the Wronskian of Y1 and Y2, and we write that as in the following way. So the notation is W bracket Y1 comma Y2. Okay, so this is the following determinant. It's a 2x2 determinant. If you can't remember that, we'll talk about it here in a second. So the top row is Y1, Y2, and the bottom row is Y1 prime, Y2 prime. And we find a determinant of a 2x2 by doing this times this minus that times that. So this would be Y1, Y2 prime minus Y1 prime, Y2. Kind of almost looks like the product rule, but it's not. Okay, and then one last thing that we'll say about that. Okay, so there's the theorem. If the Wronskian of Y1 and Y2 is not equal to 0 for any value of x between negative infinity and infinity. Okay, let me move my hand from that. So if the Wronskian is non-zero, so basically these are functions, so when I multiply this out and sort of put it together, we get a function. So if I get a function that can never ever be 0 for any value of x, then the implication is that the set y1 and y2 are linearly independent. So this is going to be, so when we sort of get to our point where we go further from here and look at the characteristic equation, this is how we're going to show things are linearly independent. Okay, so this is going to, so if we have them linearly independent, and there's 2 of them, that means they're going to make up the 2-dimensional vector space, and that's what I'm kind of aiming for. All right, this one's over.